In this chapter, we will see hourglass. Hourglass is the issue with reduced integration first order hex elements. We have seen previously that was full integration elements. Now we will see the reduced integration first order hex elements or first order quadrilateral element. So what happens when these elements are subjected to pure bending moment? Okay, so let's take this red is undeformed position of the beam. Okay, let's take this is a single element and it is subjected to bending moment M. So as we know, the deformed behavior is something like this. Okay, since reduced integration has only one integration point, let me talk about integration points. Let's recall module 3, we have already discussed this in detail. So the number of integration points n is should be greater than equal to p plus 1 by 2, where p is a uh, polynomial function in a stiffness matrix terms. Okay, so for first order hex elements, maximum polynomial order is 2. You can revisit module 3. So the number of integration points should be more than 2. Okay, so that means the two integration points are required for exact integration of stiffness matrix. Okay, and if we use those many integration points, it is called full integration. Reduced integration is one order less than exact integration required in integration points. Okay, so in this case it is n equal to 1. Okay, so one integration point in which in each eta and zeta direction is required. So total is 1 by 1, it is one integration point. Okay, which is at the center of the hex element. Okay, so this is reduced integration. Okay, now let's see, come back to the bending characteristic. As we know, in pure bending, okay, there is no shear. Okay, so as we see here from this visualization, at this integration point, the change in angle between two perpendicular lines before and after deformation is 90 degree. So that means no shear strains. Okay, which is okay. This is what required. However, if we see the bending stresses or strains, the bending stress or bending strain, as we know, it is in this direction epsilon 1 1. Okay. And the stretch happening along this line, along this direction at integration point is 0. Okay, the previous I mean before deformation and after deformation length in this integration point is same, so we can say epsilon 1 1 is 0. That means our bending strains are 0 and bending stresses are also 0, but this is not desired, right? In pure bending we should get bending stresses. However, reduced integration elements exhibit zero bending stresses, okay, when subjected to pure bending moment. Okay, let me delete this. This is not applicable to hourglassing. So this is from visualization we could understand what is hourglassing. Okay, that means zero bending stresses. So let's try to see with the element formulation similar to what we have seen for shear locking. Let's assume that say similar scenario, that displacement at node 1 2 3 and 4. So u1 is, as we know, it is displacing in this direction, so minus 0.1 mm. u2 is plus 0.1 mm U3 is minus zero point 0.1 mm, and U4 is plus zero point 0.1 mm. And Y displacements are 0. And this we have seen in shear locking, the bending strains or normal strain formulas and shear strains. Okay. So at this integration point, okay, we know the natural coordinates at integration points are 0 because this integration point is uh, at the center of the element. So using zeta and eta equal to 0 in this epsilon 1 1 2 2 and 3 1 2, we get epsilon 1 2 as 0 by substituting zeta equal to 0. Similarly, normal strains are also equal to 0. So though the element is subjected to some bending, we can see there are no shear or normal strains. Shear is 0, that is perfectly okay, but this is not acceptable. So this uh, here we can see there is a zero energy mode because bending strains are 0, bending stresses are 0, and we can say 0 strain energy, and this is called hourglassing. So once we understand shear locking, the concept of hourglassing is straightforward and very simple. So what we can do to avoid hourglassing, okay, in bending dominated problems. Okay, so this we have seen if we model, this is cross section. Okay? This is cross section of the beam. So if we have along the thickness of beam only one element, as we have seen, the bending strains are 0. What if we mesh with two elements along the thickness? So this upper green one and lower green one. Okay, these are two elements. So here we can see the along this integration point. Along this integration point, there is a compression is happening. Okay, and along this integration point, there is a stretch is happening. So we get here compressive, and here we get tensile strains, bending strains. That means our bending strains and stresses are not 0 if we use two elements. Okay. So we are here somewhat no we are overcoming our glassing issues by refining the elements along the thickness. Okay, instead of two elements, if we refine or add four elements along the thickness, this is what happens. Okay, here also we get as we can see, there is a change in length. Okay, before and after deformation at this integration point. Similarly, at these integration points and remaining two integration points. So there is a change in length. So we get the compressive strains here and tensile strains for these two elements. So our bending stresses are not 0. So C3D8R element, or in case of 2D CPS 4R. Okay, we can use these elements in bending given that we should use minimum, or we should mesh the thickness with minimum 4 number of elements. Okay, this is a minimum number. If we want more accuracy, or depending on stress gradients and uh, the requirement of stress accuracy, we can use 6 or 8 elements as well, but to avoid hourglassing, minimum 4 elements are suggested. Okay, so now let me quickly recap this chapter and previous chapter. If we use full integration C3D8, okay, full integration first order hex elements, we encounter with shear locking issues. Okay, and for that we have suggested that we should refine the elements along the length of the beam. Okay, sometimes this may not be a feasible option. And for bending problems, if we use C3D8R, okay, we get hourglassing issues. For pitch, the straightforward or simple quick fix is that we use minimum 4 number of elements along the thickness. So this is preferred element type in bending problems. Okay, as much as possible, we can use reduced integration of reduced integration elements instead of full integration of elements. Okay, because C3D8R, as we know, it doesn't have any shear locking. Okay, no shear locking. And hourglassing can be fixed by 4 number of elements. So this is more preferred element when it comes to first order hex elements. Okay. So try to use no by default no reduced integration elements in any problem. Okay, if you are meshing it with first order hex elements. Okay, so always go for this element. So in next chapter we will see the workshop on hourglassing.